Formal definition via conditional probability. Welcome, everyone. In our previous lesson, we looked at the intuitive side of independence, the simple idea that one event happening doesn't change the likelihood of another event happening. It makes sense logically, but when we move into complex mathematical problems, intuition isn't enough. We need something much more precise. To solve these problems with certainty, we need a rigorous, formal definition. Today, we are going to achieve that precision by using a powerful tool you might already be familiar with, the concept of conditional probability. We'll use this to move from a feeling of independence to a mathematical proof. Understanding the foundation, conditional probability. Now, before we jump into the formal definition of independence that we'll see in the next slide, we need to make sure we have a solid foundation. Let's take a moment to recall what conditional probability actually represents. When you see the notation P of F given E, what we are looking at is the probability of event F occurring, under the specific condition that event E has already happened. If we look at this mathematically, we express it as P of F given E equals the probability of E intersection F divided by the probability of E, provided that the probability of E is not equal to 0. To put this in simple terms, think of P of F given E as an updated probability. It is the new, more accurate probability of event F after we have gained new information, specifically, the information that event E has definitely occurred. The formal definition of independence. In plain English, we say that two events, E and F, are independent if the occurrence of one event does not change the probability of the other event occurring. In other words, knowing that one event has happened provides you with absolutely no new information about the likelihood of the second event. To move from this intuition to a rigorous mathematical framework, we express this using the notation we just reviewed. Formally, we can state that E and F$ are independent if the probability of F, given E, is exactly equal to the probability of F, provided that the probability of E is not equal to 0. Alternatively, the definition works both ways. E and F are independent if the probability of E, given F, is equal to the probability of E, provided that the probability of F is not equal to 0. Now that we have refreshed our memory on what conditional probability actually represents, let's move on to the core of today's lesson, the formal definition of independence. As we will see in the next slide, this equality is the mathematical way of saying that the updated probability is identical to the original probability. What does this actually mean? If you look at the first equation, the probability of event F given event E equals the probability of event F. This is a mathematical way of saying that the likelihood of event F occurring remains exactly the same, regardless of whether we know that event E has happened or not. In probability theory, we often refer to the original, standalone probability as the marginal probability, and the updated version as the conditional probability. So, when we see this equality, it tells us that the conditional probability is identical to the marginal probability. Similarly, if we look at the second part, where the probability of event E given event F equals the probability of event E, it conveys the same logic from the opposite direction. It tells us that gaining knowledge about event F provides us with no useful information or predictive power to help us better estimate the occurrence of event E. Now, let's take a moment to really unpack what that formal definition actually means in practice. Essentially, as we will see in our upcoming example with the coin and the die, independence means that the new information doesn't change our original estimate at all. Real-world example, tossing a coin and rolling a die. Imagine we are performing a random experiment where we do two things at the exact same time. We toss a fair coin, and simultaneously, we roll a fair, six-sided die. To analyze this mathematically, we first need to clearly define our events. Let's assign the letter E to represent our first event, which is the coin landing on heads. Then, let's assign the letter F to represent our second event, which is the die landing on a 6. By defining these two specific outcomes, we can now begin to test whether the result of the coin toss has any influence on the result of the die roll. Now that we have established the theoretical definition of independence, let's move away from abstract formulas and look at a concrete, real-world example to see this principle in action. Step-by-step analysis. Now that we have defined our events, where event E is getting heads and event F is rolling a 6, let's walk through the mathematical analysis step-by-step to see if they are truly independent. First, let's look at step 1, where we find the marginal probability of event F. This is just the original probability of the die roll happening on its own, without any extra information. Since we are using a fair, 6-sided die, the probability of rolling a 6 is simply 1 divided by 6. Next, let's move to step 2, where we calculate the conditional probability, which we write as the probability of F given E. Imagine I perform the experiment and then stop to tell you, hey, the coin landed on heads. Now that you have this new information about event E, does it change the likelihood of the die showing a 6? Well, logically, the coin toss and the die roll are physically separate actions. The die doesn't know what the coin did. Therefore, the die still has 6 equally likely outcomes, so the probability of F given E remains 1 divided by 6. Finally, in step 3, we compare our results. When we look at our findings, we observe that the probability of F given E, which is 1 divided by 6, is exactly equal to the original probability of F, which is also 1 divided by 6. Because these two values are identical, we can mathematically conclude that the probability of F given E equals the probability of F. This brings us directly to our conclusion in the next slide. Conclusion. So, to wrap up our analysis from the previous slide, we can see that the probability of rolling a 6 remains exactly 1/6, regardless of whether the coin landed on heads or tails. Because the conditional probability we calculated is equal to the original or marginal probability, we have mathematical proof that events E and F are formally independent. This brings us to our conclusion, but before we finish, I want to highlight some common pitfalls to watch out for in your upcoming exams. Common mistakes to avoid. First, and most importantly, please be careful not to confuse independence with mutual exclusivity. This is arguably the most common error in probability theory. It is very tempting to think that if two events have nothing to do with each other, they must be mutually exclusive. However, these are two very different concepts. Remember, mutual exclusivity means that the two events simply cannot happen at the same time. In mathematical terms, the probability of event E intersection event F equals 0. On the other hand, as we discussed in our formal definition earlier, independence means that the occurrence of one event does not change the probability of the other. In a mutually exclusive scenario, the events actually have a very strong relationship. If one happens, it tells you for certain that the other cannot. Second, keep an eye on the mathematical constraints. When we are working with the formula for conditional probability, we must never ignore the condition that the probability of event E is not equal to 0. We can only talk about the probability of F given E if event E is actually a possible outcome. If the probability of E is 0, then the expression, the probability of F given E, becomes mathematically undefined. Now, before we wrap up, I want to pause and address some common pitfalls. As we've seen throughout this lesson, the concept of independence can be a bit slippery, and there are two specific mistakes that even advanced students frequently make. Keep these distinctions in mind as we move into our final summary of the key takeaways. Key takeaways. First, remember that we have moved beyond just an intuitive feeling about independence. We have now learned that independence is formally defined by a lack of change in probability when we are given new information. In other words, the probability stays exactly the same, even after an event has occurred. Second, let's look at the mathematical criteria you'll need to use in your exams. You can prove that event E and event F are independent if the probability of F given E equals the probability of F, or, alternatively, you can show that the probability of E given F equals the probability of E. If either of these equations holds true, you have mathematically confirmed independence. Finally, always try to keep the core intuition in mind. If knowing that event E has happened provides you with no useful information to help you predict whether event F will occur, then you can confidently conclude that events E and F are independent. To wrap everything up, let's review our key takeaways from today's lesson. That concludes our session on the formal definition of independence. Great job today!